This is a lesson in calculus-based university physics on RL circuits, an introduction to RL circuits and its conceptual foundation. I wanted to take a second to remind us about self-inductance and inductors. The voltage across an inductor, it is a solenoid. It follows Faraday's law and Lenz's law, and we saw that the voltage across an inductor depends on how the current through that inductor is changing. Not on the current, but on the change in current. Okay, so that's an important point to note as we move forward into the rest of the lesson, because this voltage depends on the changing current. I'm also going to remind you that inductors store energy in the magnetic field caused by that current given by 1/2 Li squared. So if you are ever asked to find the energy stored in an inductor, you're just going to use that 1/2 Li squared. I'm also going to remind us that we're kind of familiar already with time dependence, this transient values through time because we've looked at RC circuits. Remember RC circuits, the charge on a capacitor is time dependent, whether that capacitor is charging or discharging. And we're going to remember that charge is a derivative, or current is a derivative of charge, and now we're taking the derivative of a derivative. So one of the important techniques that we learned from that lesson was to look at what time of interest and what that circuit element is acting like. Okay, is it just initially, is it somewhere in between, or is it after a long time? Okay, so let's just take a second and look at an LR circuit. We're going to remember that the voltage across the inductor is Li dt. I generally get rid of that negative sign because I think about, this may be a positive value or it may be a negative value. When I look at this equation, I do a voltage loop. If I just do this voltage loop, right, I'm going to have this DC battery. Notice it's a DC battery, not an AC battery. It's a DC battery. And it's delivering a current. If I do a voltage loop around here, I'm going to get the voltage of the battery. There's going to be a voltage drop over the inductor. There's going to be a voltage drop over the resistor, right? The inductor will be creating its own current to oppose any changes in current. When I write this Kirchhoff loop out, notice that it is a first order differential equation. It's a first order differential equation. And we did this before with our C circuits. We had a first order differential equation there. And we saw that e to the something value, right? E to the something t, some constant times t with a negative sign or a 1 minus will give us a solution to this differential equation. So you're going to see that a little bit later in the lesson. But what I wanted to walk us through was the time dependent behavior of that inductor as the current through it changes, like we did with the capacitor in an RC circuit. All right. So what we're going to remember is that the inductor opposes increasing current, and it's going to compensate for any gain in current. Okay. And so what I did here was I set this up in the PhET. Colorado has the PhET applet where you can set up your own circuits. And I actually just put this circuit together in the PhET, right? And so you can see that there's an inductor, there's a resistor over there, and I put this switch in, right? And so we're going to look at it at different times. When we initially close the switch, sometime while the inductor is doing stuff, and then after a long time. So right when we close the switch, remember the inductor opposes an increase in current. Before the switch is closed, there's zero current going through that inductor. And so when I close the switch and the battery starts pushing current, you can see the battery starts pushing current through the circuit, all right? That inductor will do whatever it needs to do in order to create zero current going through it, because it's opposing that gain in current from the battery. So initially, it's able to keep zero current at time equals 0. Right when we close that switch, it's going to continue to have zero current through it. And so it's creating a back current in this direction. The battery's trying to push a current downward through it, and so this net is 0. So we see that on our graph here for current, right? Zero current. The net is 0. There is a voltage over that inductor, because the voltage for an inductor depends on the voltage over the inductor depends on the change in current. So there is a change in current through there. So there is a voltage over the inductor, but there's no current through it. Okay. I know that can be confusing, because you want to say the current is 0, so there must be no voltage. But remember, it depends on di dt, which is not 0. Okay. So we're going to let this circuit this battery continue to push current into the circuit. And we're going to move over to this next column here, where we're between after the switch is closed and a long, long time after the switch is closed. Okay, and you can see this in here. The voltage, and I suggested this on the previous slide, there's going to be an E in here, an exponential, right? The battery is pushing current, and it's overcoming this inductor's ability to create a back current in the other direction. It still has a back current. It's an increasing current through that inductor. The battery's winning, basically. The inductor doesn't have enough ability to keep the current being 0, so we will get a current going through that inductor, and you can see that here. It's an exponentially increasing current. All right, so it's going to increase exponentially, 1 minus e to the negative constant times time, right? And what we're seeing is that the voltage over the inductor is decreasing. It started out with some maximum voltage, and it's going down because that current is not increasing as much through time. This value is still greater than 0, but it's smaller than what it was when that switch was initially closed. Okay. So we have an increasing current through that inductor and a decreasing voltage. As it goes through time, it's continuing to go to infinity. We can see that the current is going to go towards a maximum value, and the voltage over the inductor is going to go to 0, which brings us to our last portion of this this analysis, is that at some point, after a long, long time, the inductor will have no changing current going through it, which means that there will be some maximum value of current. And we see that over here. Whatever that is, there's some maximum value of current. And because the current is not changing through the inductor, it's not going to have any voltage over it. And because there's no voltage over it, we know that it's going to act like a wire. So if I drew the inductor at different times in this circuit, initially, I'm going to have a battery. The inductor looks like a break. There's still this resistor here, but there's no current flowing through it. So when I look at this circuit, there's only current going through the outside loop here. There's nothing in the center. As we move towards a long time after that switch is closed, we still have our battery. The inductor looks like a wire, and we still have our 2 resistors here. So these 2 resistors would look like they're in parallel to one another. These 2 branches would both have current in it. We could add those up and have an equivalent resistor, because that inductor looks like a wire in there. Okay. So when you're solving problems, that's why this chart is important, is because you're going to want to represent where the current is actually flowing, and what's actually happening in that circuit. So as we look at sort of what's going on here, Again, I told you the solution to that differential, that first order differential equation, is an exponential. And so the current through the inductor, as the current increases, it approaches a maximum value, which is what we saw in the previous slides, and it'll follow this equation. And we're going to note that it has this time constant in here, tau. We talked about the time constant tau when we were looking at RC circuits. In this situation, it's the inductance divided by the resistance. That'll give us a value of time, and so then our exponential will have a unitless exponent there. Okay. In this time, the inductor is storing energy. I would be able to find the maximum energy stored on the inductor by multiplying using the maximum current in my energy equation for inductors. Okay. Let's look at a situation where the inductor is sort of discharging, right? This was a charging, and I call it charging because it's storing energy. We're charging it up with energy. We could discharge it. So what we're going to have to do is open that switch up and let that inductor just go through those two resistors. So that's what I have drawn here. What I'm going to note is this portion of the circuit basically doesn't exist anymore. We just have the inductor and the two resistors. Okay, the inductor is storing energy, and when we remove that battery from the inductor, it's able to release that energy. Okay, so in this situation, when I initially open that switch it's going to act like a voltage supply. So let's look at that situation. We can see that the battery has been disconnected. There's no current in this branch. And we can see that the current through that inductor prior to opening the switch had a current going downward through it. And so it's going to act like a voltage supply, creating a downward current through it. And we're going to note over on that right side in that second resistor here, the current prior when the battery was attached was going downward, but when the inductor is acting like a voltage supply and this battery isn't attached anymore, that current will flow upward through that branch. Okay, we're going to notice that the voltage over in the inductor is a maximum value, as well as that current. That current is the same as before I opened the switch. When the switch was closed, when the battery was attached, it's the same value. There is a changing current through the inductor. That inductor won't be able to act like a voltage supply forever. It'll create some forward EMF, all right, but it's losing energy. Those resistors are dissipating that energy that inductor has, and we're noticing that that current is going to get smaller. You see that current getting smaller here. It started at a maximum value and now it's going towards zero. It's a decreasing current. We're going to notice that the voltage over the inductor is also decreasing. That current is changing, it's decreasing over time, the energy is getting dissipated, and so dIdt is negative. After a long time, the inductor's released all its energy. The resistors have dissipated all of the inductor's energy. So after a long time, there's no voltage over the inductor. So that's why we get it looking like a wire. It's just like an inactive element. There's no current, there's no changing current, and it's just sitting there. Okay, so that's how the inductor acts through time as it's discharging its energy. We can look at the equation to solve that differential equation. Again, like I mentioned before, it'll be an exponential, decreasing, it's releasing its energy. Okay, so if you wanted to find the energy at any point in time, the same, you'd use the current at any point in time as that inductor is discharging. Just a quick note about that time constant if you forgot. L is the inductance, R is the resistance. This is going to have units of seconds on it. And it is the characteristic time for a particular circuit. How long it takes for the current to rise 63% or how long it takes the current to fall to 37% of its maximum value. So that's a time constant. I created this summary slide for you, so you might want to take a screenshot or write it out into your notes so that you have it for when you're solving problems. Again, an important row for me is this acts like. I'm going to redraw my circuit. Always redraw your circuit so that you're representing what's actually happening, the relevant parts of your circuit. If a branch is acting like a brake, don't draw it in your circuit. It's not adding anything, so don't draw it in. As opposed to if it's a wire, that completely changes the circuit. Okay? So we're going to keep this as we move forward to solving problems, and I wish you luck on that.